Alright, let's give this a go. So I'm going to give a try. Well, I'm just going to go over the problems from this contest that I did over the weekend, and it's just a good algorithm practice. I'm going to go over all the solution to every single problem and everything. So it's the UTPC contest from September 13th, 2024. This is the Division 1 Advanced, so these are the hardest problems you can get. They are relatively, I don't know, they're just moderately challenging. They're not that hard, but I'm going to go over them. So let's get into the problems. It wasn't a good contest for me, but it doesn't matter now. I'm just gonna go over these solutions, what are the problems and the solutions to each one, and just the approach and general thoughts that I had. Okay. Let's start with this one. Okay, so the first one is spooky hallway. So on Halloween night, you find yourself in a spooky hallway lined with lanterns. Each lantern is either on or represented by 1 or off represented by 0. You can flip all the lanterns in any one contiguous section of the hallway, turning all the 1s to 0s or all the 0s to 1s. You want to get out of the hallway as fast as possible, so you want to make all the lanterns either on or off. So I say, given this example right here, the first thing you may think of is that each contiguous block of 0s and 1s, you could just flip those. So for instance here, I could flip the 0 block here, the 0 block here, and the 0 block here. So there are three 0 blocks, or contiguous segments, and there's 1, 2, 3, 4 1 blocks. And so it's not that hard to see, but your optimal choice is to flip the 3 0 blocks, and it doesn't make sense to, like, let's say you had 0 0 1 0 and you decided to flip this whole thing to 1, or, well, it won't flip the whole thing, but you flip everything here. Now you just have this 0, so you just have to do another flip to be able to do that. So it's kind of like a greedy algorithm that you're only going to flip a contiguous block, and it just doesn't make sense to flip something like this one here. It doesn't make sense to flip a block like that has you want to flip uniform blocks. I guess that's how I would say it. Uniform blocks. That is, all of them have to be the same. All the values have to be the same, which they're just 0s and 1s, but still it has to be a uniform block. It can't be a what's the word I'm looking for? Discontinuous? That's not what I'm thinking, but regardless, that is what it is there. Okay. Like I said, that one's not that hard. And the solution, I'll show my solution. The solution for me was really just to count these 0 and 1 blocks. So I just go through here, I track my previous, and if my previous is not equal to the cur, that indicates that I'm starting a new block. So when I start the 1 block, it will increment it for the 1, for that 1. it'll increment the frequency for the cur, and then it'll set the cur. So it'll set it to 1. Then when you go to 0, it'll change it to 0 and so on. So basically, I'm counting the number of 0 and 1 blocks, contiguous blocks, that is, or uniform blocks, and I just want to get the min of both of them and print that out. Yep. So that one's not that hard. Nightmare on 24th. So a little bit of a Freddy Krueger problem here. 666 megabytes for the memory limit. That's curious. 1.3 seconds for a time limit. That's also weird, but you know, this is the number of the devil or something. And you know, you got this. So the crux of the problem is you have in buildings along the 24th with the ith building housing this number of students. Freddy is curious about the logistics of impossible quantities for the number of students he would visit, where the jth possible quantity is given by cube sub j. When meeting students, Freddy must visit the students' buildings in sequential order, starting with the first building. So he must start from the first building. So I'm gonna go over what that means. But he's curious about the minimum of buildings Freddy would have to visit to check that many students. If it's not possible to meet the request number of students, print this. So here we go. We're going to be given the number of students in each building, which could be 0. And in this example, you can see we have 10, then 8, then 2, and 4. And then here's your queries, 10, 15, 25, 41, and 100. For each query, basically, he only has to go so many buildings so that he can match with that many students. So I don't know. I don't think I have to go into this one too much, but let me take this example. But basically it's prefix sum. Really, that's all. It's just prefix sum with binary search. So given this example, all you have to do is calculate the prefix sum. So say you get 10, 18, 20, 24. Wait, is that right? Yeah, 24, 28, 36, 45, okay? So when he queries 10, he just needs to visit one building, right? If he visits the first building, he'll be able to scare 10 people. If he needs to do 15, he needs to do this building and then do this building, which gets him over 15, but it doesn't matter if it's over, but you want to find the first number here that is greater than or equal to this, right? So yeah, so you have like the 10, you have the 18 here, then you have like 25, so 25 would have to go all the way past this one, would have to go to here, to 28, so 1, 2, 3, 4, 5, and then 41 would have to go to the last building, and 100 would be impossible. So yeah, you could just binary search that. You can see 1, 2, 5, 6, 7, 8, 9, 10. So if we look at my code for this one, so you can see I calculate the prefix sum right here, and then you go through the queries, and this is like an edge case, I guess. I forgot about this one. So if Freddy only has scares 0 students, so that's right. So not only could this have been 0, but this also could be 0, the query. So then he doesn't have to visit any building, so just output 0. Otherwise, you just want to output the lower bound. So you want to output just when it's over, or, you know, and basically if it goes out of bounds and you know it's impossible, it's -1. Otherwise, it's the answer, but increment by 1. So that's that one. Okay, candy eating. This one this one's interesting. I didn't get it at first when I read it. I came up with a solution that was not the right solution. The candy that Charlie has can be divided into n types, number 1 to n. For some candy type I, let Ki denote the amount of candy I that Charlie has, and let Ci denote the tastiness of each piece of candy type I. The total tastiness of Charlie's consumption is given by the sum of the tastiness of each piece of candy that Charlie eats. Charlie would love to eat all the candy he has, but unfortunately there are following restrictions. So all the candy expires after some number of days. So you can only eat it for, if D is 5, you can only eat candy for 5 days. Charlie's parents won't allow him to eat more than X pieces of candy in a given day. There's a limit to how many pieces of candy, and he cannot eat 2 candies of the same type on the same day. So when you're eating X pieces, they have to be X distinct pieces. Please help Charlie determine the maximum total tasting he can achieve. Okay, so N and D and X are all less than or equal to 200,000, and then you give it the amount of candy and the tastiness of each candy. 1 and so on to 200,000. Okay, so let's take an example here. And this is NDX. Alright. So I'm just going to point out for this example, D is 3 and X is 3. So first thought that I guess I had in this problem is, what is the optimal way I could maximize the candy I eat? Well, if you think about it, the candy in here that is the most tasty, that one is the most, it contributes the most to the total tastiness. So it makes the most sense to that, so I start thinking instantly there's some type of greedy algorithm approach here, some type of sorting in terms of what I want to have. And you might say the sorting is simply this, is like just take the largest one, 9, 8, and 7, because I can take 3 distinct candies, so I'll just take the candies with 9, 8, and 7 tastiness, and it says the count of them is 1, 1, 1. So you might think, okay, well, use some type of you sort the candies based on tastiness, and then maybe use some type of min heap to track when you will no longer be able to take that candy. But I'm going to go over why something like that doesn't really work with an example. So with a counter case. So the example I just said is basically this, is you sort the candies, right? So you sort and you have descending things. So if I sort it, I get 9, 8, 7, 6, 5, 4, 3, 2. And we have a certain many of these. You have one of these, you have 2 of these, 3 of these, 2 of these, 2 of these, 1 of this. So it takes these first candies. So on day 0, you pop these candies into your thing, and then you put into some type of min heap the day on which it expires. So these candies will expire, and you just put the index. So I don't know, 0. I sorted it and then indexing it, which is kind of weird. You probably wouldn't do that. But yeah, no, these all expire on day 1. Sorry. So all these candies expire on day 1. So when it goes to day 1, so you start with day D equals 0, and then you go to day 1, and you're gonna stop at day after day 2, right? Because 0, 1, 2 is actually 3 days because we're starting from 0. That hopefully is not confusing. So anyways, on day 1, these values are equal, so it's gonna pop all these out, and it's gonna say, hey, I have X slots available. So okay, it's gonna take the next 3 largest, which are these, and it's going to add the days to them. So this one will expire on 3, this one will expire on 3, and this one will expire on you know what, the index doesn't matter here, you just need to put the value here. 5, 4, 6, so 3, 6, 3, 5, and then it's 4 will expire on day 4. So in that regards, this is like a min heap or something. So then on day 2, your score will still be the same. You might say, okay, that does give you the correct answer for this example. But there is a problem with this approach. You need a slight modification to the greedy algorithm here to solve it. And that is basically, let me try to get an example here. Let's see, I need to come up with an example. Let's say you have 5. Sorry, I'm going to try to come up with this on the spot. Alright, so I have an example. Yeah. Alright, let's imagine you have these candies. Took me a while to come up with the example. Okay. But I think this is correct. So the example is this. Imagine I have the candies. I'm just put the tuples here. So this is the tastiness, and then this would be the count. And so imagine for a second that, x is equal to 2 and d is equal to 8. Okay. So, the current strategy, it would take these two first, and it would fill in the first slot, right? So if you imagine kind of like this. Hold on, sorry. So you have two slots available. And so all the way up to 4, you're going to schedule the 8 here, and you're going to schedule the 7 here, right? Because you think, oh, that's optimal, because these are two, I want to make sure I eat these candies all the way up, right? But then if you schedule the 5 here, if you notice here, you only have 4 days remaining, which means you have 1 candy left over from the 5, and then you can schedule your 4 here. But really, is that an optimal way of kind of organizing this data? Compare that to if you did this. Okay, so let's say you take your 8 for these days, okay? And then suppose you actually eat your 7 on these days, right? I mean, it fits in there. That's 4 of them. Then you could eat your 5 right here, and then you could eat some of your 4. This is actually better because now you get 8 times 4 plus 7 times 4 plus 5 times 5 plus, I guess 4 times 3, whatever's remaining there. But up here, you're getting 8 times 4 plus, okay, so this part's not different, but you only could get 4 times 5 and 4 times 4. But this one's far superior. It's better to have taken a 5 here than to have taken an extra 4, right? An extra 5 is a plus 5 compared to an extra 4, which is a plus 4. Like, we prefer the plus 5. So in this example, I'm just showing that like my first instinct was not really correct, and it took me a bit to come up with this approach. So really, you want to pack it in this way, which is a different way of packing it. It's still a greedy algorithm, but you're kind of packing everything differently. And so my idea is essentially you sort all the candies by tastiness, but then you layer it in. You imagine that these are like the days are one dimension, and you imagine the number of distinct candies you have to eat as another dimension. So I imagine it as like a matrix. So I imagine it as like a matrix, where you have your D and your X dimension. And basically how I layer it is I take my highest value candy and I layer it here, right, since my first one. And then I take my second highest, and maybe it goes here. I layer it in there. Then I take my third highest, so let's say this is 1, 2, then I take my third highest, but let's say it goes all the way to here, like this is my third highest, but it's kind of layered, right? Because this does not go against the constraint. Like I can have 1 and 3 both layered. I can eat both of those candies consecutively. And when I'm writing these down here, I'm saying that 1 is greater than 2, greater than 3. Okay, everything is going like this, or I think greater than equals possible. So so on. And then you could have maybe 4 here, and then maybe you could have 5 here, then maybe you could have the 6th here, and then maybe you could have the 7th here. I don't know, maybe you have 8, so maybe 8 goes all the way here. So notice one thing, you can't have 8 go, okay, let me show what's not possible. So this is not allowed, because now this candy is overlapping. So at most, you can take only up to a certain point. So really, you can only take this much. If you have more candy than there are days, you can't possibly take all of that. But anyways, in this way, this is the optimal algorithm, the greedy algorithm. So I hope that kind of makes sense how you're kind of layering it. Kind of like a matrix. You're layering in a matrix, and you're kind of just filling in the row by row. if that makes sense, row by row, take a candy, take all the count of the candy up to the number of columns of the matrix, and then take that candy, and then it moves it, over to some point. Excuse me, and then it goes to the next row and so on, and you just keep layering the candies in. That way, it corrects for this case here. And yeah, I don't know if that makes the greatest amount of sense. Okay, so I keep track of the counts, the values, and the candies, which I have value count because I want to sort based on that. So I construct these candies so that I can sort them, but I want to sort them in descending order. I want the tastiest candy to be first, the one with the highest value. So I have my answer, I have my day, and I'm just going to go through these candies in sorted order. And then I'm going to note the start day, and I'm going to note the take, which is I can't take more than, I guess, more than the number of days I have, right? Because the D corresponds to the number of columns, so I can't take more than the number of columns. But I can only take up to this, so it's got to be the min, right? I can't take more than the number of candies I have available, but I also can't take more than the number of columns. So you may fill into the end of the last column, and then you just update take, you update your answer, you update the number of candies remaining, and you check if D is equal to day, because that means you're going to start in a new row. And instead of starting a new row, I just do this. I decrement X, basically, because I have a certain number of rows, and I just keep decrementing until, I don't have a row. So if I don't have a row, it breaks, as you can see here. But, if there's another row, I can take basically up to the start or the candies. That prevents it from taking more than the number of, that prevents you from going to the situation where you're going to be taking the same candy on one of the days. And then you update your answer in the day. So that's the algorithm. I think I could have done this a little different using modulus and remainders probably. But this is easy enough to implement. Okay. So hopefully that one makes sense. I think that was the hardest one to understand, to be honest, for me. Out of all these problems, that may have been the hardest one. Haunted house. This one was very straightforward to me for some reason. So fortunately, Harry knows the layout of the house. So you're in a haunted house, you're afraid of ghosts. There are K exits, and it gives you the rooms where there are exits. And Harry has a room in S, was in room S. He found out there were exactly G ghosts in the house, specifically there in rooms. It takes 1 second for both Harry and ghosts to move between rooms. Also, it doesn't say here, but ghosts can also wait in a room. They don't have to move. An exit is considered good if it is guaranteed that Harry can get to the exit without ever being in the same room as a ghost. Please tell Harry how many good exits there are. So basically, you're given the size of the grid, and you're given the start location, and you're given the number of exits and number of ghosts. It's all within 200,000, and then you're going to be given the door that connects 2 rooms. Really, we're going to think of this as a graph. Like, this door is just connecting 2 rooms. Well, the rooms are really just nodes in the graph. So this is an edge. And then here you have the specific rooms or nodes that have exits, and specific rooms or nodes that have ghosts. Okay. And at most, 1 door between each pair of rooms. So it's kind of, I think it's saying it's a graph here. So is this one doing this? Okay. Let's just do this one. Try to run. Okay, so you can represent this as an undirected graph. So it's cool. So you can say, basically you have some type of graph here. I guess it could be whatever. And for this graph, there's a ghost in some locations, like, okay, ghost might be here, or ghost might be here, you know, I'll just do 2 ghosts. Maybe there's an exit here, an exit here, an exit here, and a ghost here, and so on. So I'm gonna say the basic algorithm. So the basic algorithm is you kind of want to use breadth first search, but what I thought to do was the following: is take all the ghosts, and then perform a breadth first search from them. So kind of do like a multi-source breadth first search, which really just means you start with multiple nodes in the queue, and then you just search out, and then you just track basically the shortest distance for a ghost to reach each node. So I just find the shortest distance for a ghost to reach each node in the graph. So for each node, you'll know the following. You'll know the distance that it takes for a ghost to reach it, right? For any ghost, doesn't matter which ghost, any ghost to reach it, and that's why you do the multi-source breadth first search, because that's pretty fast. That's gonna be fast enough. So okay, you do that, and then you need to find out which exit you can visit. So then you take the person, so wherever they start, maybe here, and then you do another breadth first search, and you find the shortest distance it takes for the person to reach each exit, and you use that to basically compare. So basically, the argument is if you know the shortest distance for an exit like this is u, and you know that the distance is less than the distance of u, that means you can reach the exit before the ghost can reach it, which means it is a reachable exit. If it is the other way around, then you can't reach it. So that's the basic idea. So I'll show the code here. So multi-source BFS. So I build a adjacency list, the graph that is. I build the exits, the ghosts, and then I calculate this distance for ghosts and this distance for the person. And I do the breadth first search using the distance for the ghosts and using the ghost, so it's a multi-source breadth first search. So what that will do is it will do the breadth first search, implement all of the start locations, and set the distance to 0 because there's already a ghost at a location. So it takes 0 units of time, 0 seconds, and then push them into the queue, and then this just goes through the breadth first search and just checks that if it hasn't visited this, then visit it, and and it's just I'll do that. And then really you set your person. Your person is like actually a single source, but you can reuse the same algorithm just with a vector of one element. And then this does the same thing. And then you just have to go through each of the exits and see, can the person reach that exit before the ghost can? And then you increment the answer. And that's basically it. That'll tell you how many exits a person could possibly reach before any ghost. Okay, I'll move on to Pumpkin Patch. Okay. So this one was also a bit straightforward. I kind of figured it out in the contest. I had like one small bug. But yeah, this one's also pretty straightforward. You have that you're given this grid. In the grid there are many items. There's an empty space, there's these impassable pumpkins, there's a candy corn, which actually Sam can collect by passing through, and then there's jack-o'-lanterns, which Sam can only pass through by spending a candy corn. And then S, which denotes Sam's starting space, and then E, which denotes the exit. So the goal is, Sam can only move in 4 directions. You want to output the shortest amount of time it would take for Sam to reach the exit space, or if it's impossible, then you print out spooked. So essentially, it's kind of similar. It's kind of like a breadth first search again, but breadth first would be the best search through the grid. But there's a little bit catches to it. One thing to note is, and I don't feel like it explicitly says it, but the candy corn, you can't collect multiple candy corns. So if you collect a candy corn from a grid location, you can't collect it again. But anyways, if you look here, you can see that it says the number of candy corns in the maze is at most 8. That's interesting. So you might, that kind of gives you a hint at that you might be able to use a bit mask to represent which candy corns have been collected. Because a bit mask, the reason why is because 2 to the 8 is really small number. I think it's maybe 512 or 1,000 or something. But yeah, it's not that large. Or actually, no way. That's no. It's more like 128. I think it's actually really small. I'm quite a bit off. Oh yes, 256. Okay, never mind. I was a bit off. Okay, but anyway, so back to the problem here. So this is example grid. So the idea really is, I don't know if I can take this one. Alright, I'm going to go over the idea here. So the idea is that if you just think about it real quick, as we move through the grid, if I'm in a cell, let's just like put myself here. So let's say I'm currently occupying a cell here, right? The cell is noted by the row and the column. That's how you identify it. And that's kind of what you do. And I kind of want to find the shortest distance. So you're thinking distance RC, right? And you want to find the shortest distance to reach a cell. And that's kind of the normal breadth for search. So if you imagine this problem and it had no jack-o'-lanterns, no candy corn, all I had were pumpkins, which are essentially acting as obstacles in the maze or walls in which you cannot pass, which are impassable. If you imagine it like that, it's just a simple search through the grid, finding the shortest distance, and then using this to represent the shortest distance to reach that location. But given you have the candy corn, what may you need to track? Reaching this cell, you could pick up a candy corn somewhere along the path, or you could not, right? You could pick up some subset of candy corns or not. And it kind of matters if you pick them up. So you're going to include in here a mask. And I'm not really going to go over what a mask represents, so if you don't know bit mask, then that is something to understand. But this is like representing which candy corn. So basically I create an identification for each candy corn at each location. And so like this bit mask right here would represent that the first, and this is 0, the first, second, third, the third and the 5th candy corn have been collected. That's what this would represent. But then we need one more thing, because each time you go to a J, pass over a J, you need to know if you have a corn that you collected that you can use. But once you use one, it is consumed. So the other thing you want to do is you want to track available or unused corn, right? So this is just an integer. And this is what should represent your space. So you want to minimize on this. So it's like a slight difference to the normal BFS, where you kind of want to minimize on this. So for any cell you want to do that. And so you have to think, is this possible? Well, this is 100. This is up to 100. This is up to 2 to the 8. And this is up to 8. So really this should be fast enough, given that these are all small values. And so yeah, that's what I did. look at the code. So yeah, so I use enum to represent each of the cell location. I create a location object, so rc mask and count, the grid, and then this is the distance. This was actually my bug. I had an 8 here, but it needs to be a 9. That was one of the bugs I had that was annoying me. And then this is just a map of corn, so you can identify them or convert them into integers, right? You represent the row and the column where the corn exists as an integer. And then the neighborhood, which is just where I can get the 4 directionality, get the neighbor each cell with which is the neighbor cell that I can travel to. And then inbound is it inbound or not? And then we continue going on down into here, and you can see in here you initialize everything to infinity for the distance matrix, or the distances for each state. I create a grid with the enum type cell, and then it goes through here, and it just, if it's P, it does that. If it's star, it adds it into my queue, because I'm going to begin a breadth for search. Queue is a very common thing to use in breadth for search. Set the initial state to 0. Do all these, and do the same with the corn, so I can keep identifying each corn. And then in the queue, you have your row, your column, your mask, your bit mask, and your count, which is the count of unused corn. And then here, if it's to the end, you output. This would be the minimum number of moves to reach the end. And then here you travel through the neighbor, and if it's a wall or if it's not inbound, you continue. If it's a jack-o'-lantern, you can traverse on it only if you have some unused corn that you've collected, and you would only do it if you have not visited this one yet. So if you've already visited, then you've already visited with then minimum moves. So with fewer moves. So this is a worse path you'd be taking. So yeah, so then it does that, and then you have the corn here as well. So if it's corn, you get the CID, and you check if you haven't already collected the corn, because you can't collect the corn more than once. If you haven't, then you check if this is the shortest path, and you increase the number of unused corn because you haven't used it yet, and you do the same thing. You update the distance, and if it's an empty cell, you traverse to the empty cell, increasing the distance. Yeah, so on, so on. You see how it's spooky if you can't reach the end, and so on, so on. For instance, like jack-o'-lanterns in the way, or pumpkins are in the way. And so the only thing I'm say here is that this is like it's like a hard. Let me tell you my thoughts. It's kind of like, I feel like this problem is a little challenging at first, because you're doing a breadth for search through a grid, and you kind of have to track some things of your state. It's not a normal breadth for search through your grid. It's a breadth for search through your grid where it matters what specific cells that you've passed through where you were able to collect something from that cell. It matters which cells you've visited in the past. It matters how much of some item you haven't used to pass jack-o'-lanterns or whatever. So the state is just a little more, there's more variables in the state. I don't know. I don't know if that makes sense. It makes it easier to, I'm just trying to think aloud. Okay, this one. So this one I did not figure out until post-contest. I didn't have time. Like, I read it in the contest, and I guess I was kind of tired after struggling on these ones, which I shouldn't have. I don't know. But this one turns out to be maybe the easiest one. When you read it, it seems hard, but it's honestly maybe one of the easiest problems. So there are N students standing on a speedway. They each have some position, and each student randomly faces either left towards position 0 or right towards position N, with equal probability, independent of any other students at time equals 0. Each student begins to move 1 position per second in the direction they are facing. If 2 students collide, they switch direction without stopping. 2 students may start at the same location if they move in the same direction. If they move in the same direction, they never collide. Given Q queries of T, each asking for probability that no students have exited speedway reaching position 0 in after T seconds. Determine the result for each query. It can be shown the probability that no students have exited speedway is either 0 or the form 2 to the negative n. We'll go over that in a minute. For some integer m, you should output n for each query. If the probability is 0, output -1. Okay, then Alright. So, how do you do this one? What observations do you need to make? Okay. So, the first observation is this. When it's talking about things colliding, you can, in a sense, ignore that. So, let me explain here. So, let's say you have something like this, right? And let's say you have something here that's going in this direction and this thing going in that direction, right? Say this is the red one going that direction, okay? Yeah. Let's say it was going that direction, okay? So in the next turn, they're going to be here, okay, at the next second. At the next second, what's going to happen? Well, this is going to be here, but it's going to be going the other direction, and this is going to be going the other direction. But really, you can just, since they bounce off each other, you can just pretend that this one goes through the other one. It's literally, it's the same thing. Sounds weird, but it's the same thing. You can just pretend that this one passes right through it. So the collisions you can actually ignore. And if you have, so here's the proof. If I have this grid here, and I have this, right, and I want to know how long it takes me to reach the end here, and let's say I have something here going this direction, so it's going to take it 1, 2, 3, 4, 5. It's going to take it 5 seconds. Does there being something going the opposite direction affect the time of something reaching this in 5 seconds? It doesn't. So that is, if this person goes here in 1 second, and but then it collides with this one, which forces this one to go in this direction. So then the red one will go in here in 2 seconds, and then 3 and 4 and 5. So it's the red one, because it collided and it swapped direction. It's the one that will reach it in 5 seconds. But you can, and what's interesting is that the white one now, how many seconds did it take this one to reach here? 1, 2, 3, 4, 5 as well. The white one will reach this in 5 seconds after it bounces off and collides. So you can actually ignore the collisions entirely. You can just say this ball here will take this long to reach this, and this one will take this long to reach this. Given that maybe that doesn't exactly make sense, and maybe it seems kind of weird, and you might have to do other examples to get that the collisions aren't important. But that's the first observation here. Given that observation, we kind of have a grid here where we have, I guess, 0, 1, 2, 3, 4, 5, 6, 7. I don't know if I have 7, but I'll just write 7 in. So we kind of have, not a grid, but I don't know, that's from the last problem. But you just have this number line. I mean, I'm representing it as an array here, but number line or something, one-dimensional. So okay, so we have a ball here, and a ball here, and a ball here. I'm going to ignore the fact that there's duplicates. That goes good right now. So let's say you just have these balls here. So let's go over some queries we can have. We can have a query of, I don't know, and so it exit the speedway at these. These are the exits. So we could have a query that is 1 second. So if the query is 1 second, if this ball is facing this direction in 1 second, it will reach here and it's safe. And if it goes this direction, it doesn't matter. So I'm going to make a statement. These two balls, it doesn't matter in which direction they are facing, they will never exit this. It reaches 0 or low 7 within 1 second. For this ball, though, it's different. If it faces this direction to the right, it will exit. So you say, okay, well, so there is a chance, right? So what is the probability? Well, what is the probability that this ball faces in the right direction? There's half. It's 1/2, right? Because there's 2 options, and there's half probability that it will face in this direction. So there's half probability that it will exit. Does that make sense so far? Okay. So for this, there's 1/2 probability, or that's the same thing as 2 to negative 1. Okay, so if we take t equals 2, how does that change? So now all of a sudden the 6 still can't go to the right, but the 2 can't go to the left now. So now you have 1/4, or 2 to the negative 2. And if you go t equals 3, you say, okay, can the 3 go over here? Well, it can't go over here, but that's okay because you can just have it, well, yeah, it can't face this direction now. So you get 1/8 or 2 to the negative 3. So this is what you would output, by the way. That's what it means by output 2 to negative m, but just output the m. So, okay, so we have that, right? Now just imagine you had more. So imagine you have 2 balls here, 3 balls here, and 2 balls here. That just ups this to 2 to the negative 2. That just ups this to 2 to the, and this is 1/4 now, and that just ups it to 1, 2, 3, 4, 5. There's 5 balls, and then this one becomes 2 to the negative 7. Sorry, as well, because now there's 7 balls that can't, that you have this thing. Now, if t is equal to 4, you're in trouble because this ball right here, it will reach, or sorry, the balls at the 3 location, in time 4 they'll reach the exit here, and in time 4 they'll exceed the exit here. So therefore there is no direction that these balls can face to which they will not exit the speedway. So this is when you have 0 probability. The 0 probability that they will not exit. Sorry, this is the probability that they will not exit. Right, I think I mixed that up, but so sorry, I said these are probability that they exit, but this is actually the probability that they won't exit because you need it to be facing in this direction. So there's only one of both the possibilities, and you multiply them, right? So it's 1/2 times 1/2. It's like you can only use this direction and you can't use that direction. So there's only half the directions you can pick, half the directions you can pick. And so what it turns out is really the only thing you need to calculate and keep track of is in this array is you're going to want to sort it, and then all you have to do is calculate the distances. So this one is distance 2 to the left to the 0, and then it's 7 minus 2, 5 to the other ones. And these are 3 and 4, and these are 6 and 1, and that's all you have to calculate. And then all you need to do is take the smallest number of each one and put them into an array and sort them, and it will have duplicates because again you have 2 balls that are at location 6, and then you have this many and this many. So now when you query, this is index 0, 1, 2, 3, 4, 5, 6. You can just binary search and find the first number that is greater than. So like for t equals 1, it will return 2. Well, that's correct. For t equals 2, it will return 5. Oh, well, that's correct. And for t equals 3, it will return out here, which is 7. Oh, that's correct. But if it gets 4, you have to return 0. So I just say this is the threshold. That is, take the larger element and calculate the min of these, right, which is 4. And so let's look at the code, which may make more sense. So yeah, you have the threshold and you have the position array. So you have the threshold. So each time you read in an integer, you calculate 2 values, the u and the v, which is distance from to the exit on the left side and distance to the exit on the right side. And then I just keep it so that u is always greater than v. I'm sorry, u is always smaller than v. So u is the one that I'm going to push back into the position, and then the other one I'm going to use to set the threshold, which I want the min of the max. If that makes sense. Sort the positions, and then basically that's it. If it's greater than the threshold, you return -1. Otherwise, you do the upper bound. Okay. Let's move on to the next one. I don't know if that one is completely clear. I am wanting to get these done in like just over an hour. So this one, trick or treat. This one also looked difficult. Yeah. Okay, this one also looked difficult when I first read it, but turns out to be rather simple. The trick that could solve it. So basically, you're given a one-dimensional array, and Alice wants to do trick-or-treating at all these houses that are on this one-dimensional array. However, for each of the house on the one-dimensional array, some of the houses will turn off their light at some minute, after some amount of minutes have passed. So the minutes start at 0, and then as the minutes count down, so like if it's 5, Alice has to reach that house before 5 minutes, so at 4 or less. So the question is, can Alice visit each house before they turn off the lights? And if she can, what is the minimum amount of time it would take her? So the interesting thing is, N is 2000, and K is, and AI here is between 1 to 10 to the 6. Okay. So, how would you solve this? So, I'm not going to go over an example, but I'm just going to say, really, I think it's the first thing you might think of, or you could possibly think of. I mean, it's this. It's basically this. This is that, first off, you have this one observation, which is if you start at a location and you travel to reach the house, and then you go back and you travel, because you're gonna like, so if I'm at this house and I want to reach this house before some time, I'm gonna move in this direction, right? And as I pass each house, I will do trick or treat, and I will cover those houses, and they will be done. But then, let's say I need to reach some houses over here on the left side that were to the left of this. Well, okay, to reach those houses, I have to travel back through all the houses I already visited, and then I can start getting those houses. And now let's say I need to visit some more houses that were to the right of this. So I got to go over here. And you might do the same thing again. But there's a lot of wasted time in here. And you want to minimize the time. So what I thought was, you can represent the range with some L and R variable. And so what I was thinking was some type of DP here, or something, where you have your range L to R. But that doesn't give you the full information, right? Because this is the second observation I made, which is that you will either be on the left endpoint or you will be on the right endpoint. You're not going to be somewhere in between. So the other thing you want to track is your position. Okay, but your position, your position will be an element of L or R, right? It's not going to be anything else. It only has 2 possible values. So truthfully, it's like a binary. It's a 0 or 1, right? It's on the left side or on the right side. So if you think about this, the space that you have is O of n squared, essentially, at this point. And since n is 2000, you can start thinking, okay, this might work. And then basically, this is kind of what you want to do. And for each of these, you want to minimize the amount. Oh crap, I'm writing this real bad. Minimize the amount of time. Okay, so that's easy enough, right? And you know your starting position, which is whatever K is that it gives you. So your starting position is like this. Position doesn't really matter. It's going to be K. So that's your starting state, and your time is currently 0. So now you can explore. So here's the question: what are your transitions? Okay. What are your transitions? So if you have this thing here, your L and your R, and let's say your pose is here. So you have DP, L and R, and pose. So the transitions are you can move one more to the right, okay? So I could go to L R plus 1, and then pose will be R plus 1, and then that will be equal to this plus 1, right? You only travel one more unit of time, okay? But there's another option you could have, because sometimes you may have to do this. I'm not throwing it out. That's something you wouldn't have to do. Suppose I need to travel to something over here. Well, I can do that, and then I would go to this state, and then the range would be like this, and this would be my new position. And right, instead of adding 1, you traverse this entire distance. Well, that distance is just R minus L plus 1. That's just the distance of the segment. So these are the two transitions I could come up with. Either you're gonna extend on the left side, or you're gonna extend on the right side. And this is if your position's on the right side, and then vice versa, your position could be on the left side. So yeah. So how do you do this though? How are you going to do dynamic programming and make sure that you're minimizing the amount of time? So basically what I don't know, this is what I thought. Just use a min heap. Just use a priority queue. Just do something like a Dicer's algorithm. That way it will continue to traverse the segments that have the smallest value associated with it. So it will find the minimum value. But by using dynamic programming, you prevent yourself from like revisiting, and you keep the time complexity down to be really, really good. So I'm going to show how I solve that. So I created a state to represent the LR pose, and V represents actually the amount of time, and the pose is the position you're at. And then I have this Boolean operator that is going to be used because it's going to be using the min heap priority queue. So I just want it to make sure that it keeps, if V is smaller than the other value, it wants to keep that one in front. Okay. That's the minimum value. Okay, so then I do this. Okay, this is a handy function that takes in the length and takes in the left and the right endpoint, and I'm not going to make it require it that R is greater than L. Instead, if R is not greater than L, it'll just swap and it will calculate the length. So L does not have to be less than R. And here, I read in my variables, I subtract 1 because I'm zero indexing everything, so my start position is 1 less. And then it creates the min heap with the original start location, and then the V. This is the value, right? This is the thing that is going to sort the min heap on. So then you just go through the min heap, and then if the length is equal to n, then you've reached the end, and that is when you're going to return the value. That should be guaranteed to be the smallest value because you used a min heap. And then these are the transitions. This took me my second attempt to come up with this, but basically, if you can extend the right side, try to extend it if you can, and all you have to do is use the length of your current position in R, and that's what you extend by. It's either going to be 1 or it's going to be R minus L plus 1, and then you do this right here, and then then you say, okay, this is your new position, right? R plus 1, V plus the length. Otherwise, can you extend on the left endpoint? Then you try doing that, and you add the value, the cost of doing that. The cost. I keep saying value, but I think it's better to say cost. Okay, that's just over an hour. I did want to go over the last problem. Here, I did want to go over this one. Phantom poker. See if I can go over this one real quick. and to poker. So essentially you have these integers that are between 1 to 13, and the specific combination you want, which is you want it so that the product is equivalent to 5 mod 13, which just means that the product's remainder when divided by 13 is 5. So here's an example. This 2 times 5 times 7 is 70, which is 5 mod 13. But he's met with these challenges, which are update challenges, like changing the value of a card, and also these challenges of querying a range and finding the number of combination of cards using only the cards in that range, and that every 2 cards at different indices are considered distinct, so the same value but different indices is different. Alex is stunned. How is he going to leave now? So anyways, yeah, I don't know. You have to put the answer module of this. It can be really large. Now you're given the n space separated integers, which are the initial ranks of each card. Yeah, and the next Q line is containing a query, one per each line. Each query is given the format described. Okay. Fair enough. Anyway, the idea here is, so the first thing that I really thought was, well, sounds a bit kind of weird to me, but, so the idea is you have these point updates, and then you have these range updates. And so you can use this, you can use something. You can use this following fact. If I have a value, let's say I have 2, let's say I have 2 and I have 3 ways to get to 2. So imagine I have imagine I have 2 segments. A segment over here and a segment over here. And in this segment it may have like 0, 1, 2, 3 all the way up to 12. 0, 1, 2 all the way up to 12. And then for 2, maybe over here it has 3. And then over here for 3, maybe it has 4. If you combine these 2, that is, you say there's 3 ways over here, and there's 4 ways over here to be able to get 3, 2 over here. So imagine if you combine these 2 together. Well, if you combine these 2 together, you're going to get 2 times 3, which is 6, right, because you're doing the product. So it's going to be, you're going to multiply 2 times 3. And then you see how many ways can I do this? The number of ways would be 3 times 4, right, because there's 3 ways I can get a 2 over here, and there's 4 ways I can get a 3. So that's just 3 times 4 ways. So when you see that, what you may realize real quick is that I can go through here and I can take any of these. Like, what if I had 10 here and I had, oh wait, no. What if I had 5 here and I had 2 of them? And I take the 3 and the 5, the 3 from the left and the 5 from the right. So 3 times 5 is 15. Okay, 15 isn't important because we're doing everything in mod 13. So what's 15 mod 13? It's 2. So really you take 3 times 5 modulus 13, which is like 2. And then you take the number of ways to form this 2, which is 3 times 2. So really what you can do is you can loop through these 13 2 times, and you can merge these two like adjacent states. It's just O of 13 squared, which is constant. And it just goes through and it updates everything. And I don't know if you can see the idea here, but that the update is I times j mod 13 plus or equal the left and the right, so a left I times right j, which is number of times you can do those both, and you just add it to this, right? So A is whatever you're going to return for the new merge segment. So you can what just happened? You can have a okay. So you can merge. Oh my gosh. Okay, I'm trying to do this on. It's a bit challenging. I need to. Yeah, it's a little hard to do it while I'm trying to do it. But anyways, yeah. So you have this, and then you have this split one, and you're gonna create the larger segment. So you're gonna combine this half and this half to get the larger segment. So anyways, what you can kind of see is that basically you can use a segment tree, and you just need to keep track of the count of everything. And I'm not going to go over all the details of that, but yeah, it's essentially something like that. You use a segment tree. You do have to do like when you're updating a value, you need to set it to 1 for 1, and then whatever the value is, set it to 1, because there's always a way in which you don't take an element, and if you don't take an element, it contributes exactly 1. 1 is like a neutral value for a product, right? 1 times, it's the identity element, that's what it is. It's the identity element for product. Yeah. Okay, let's look at the code. Might be a little hard to read it because it's going to be segment tree. But yeah, so you have the segment tree here. I'll go into details for that. That's really the crux of it. But here you use a segment tree. It's very, initialize segment tree. You update it with the index and the value of the card, the rank. Read your queries, read your left, right. If it's a query type 1, then you update it. You update the rank for that card. Otherwise, you query it. Okay, so that's easy enough. But now you have to implement the segment tree, so we'll go over that real quick. So basically what I did was, instead of having, I have a 2-dimensional array for nodes now, where basically it's the number of rows is, or the number of arrays is basically the nodes in the tree, but for each node it's going to have an array of size 13, right? It makes sense because you have 13 values, and you want to, and what those represent is that vector of 13, the index, whatever it may be, like 2, and the value at the index represents the number of ways, the number of combinations in which you can get a product equal to that index 2 modulo 13. Right? So initially you want to set it, so for 1, you want to set it to 1 because it's the identity element, so that is like you're saying it won't affect the value. And then you are going to do this, so you're going to do the update. So the update is like what I said, you set everything to 0 again for that segment index, and for the I, so for that node you set, so just imagine taking a node, and in particular it's taking a leaf node of the segment tree, and it's going through the array from 0 to the 12, and it's setting it to 0, and then you're going to set 1 to 0 again, it's this identity element, and you have the option to not use this element, and then you increment by the value, So there's that, and then when it does ascend, it's going to combine. So combine is very important. How is it going to combine these two? Because it's going to do the combine when it's doing the ascending up through the nodes to the root node, and then it's also going to need to do it for the queries. So what is combining going to do? It's going to take 2 vectors, which are going to be a size 13. So these are the vectors associated with the node. and then it's going to get the result, which is set to some neutral element, which I think is 0 right now, and it's just going to keep adding to the result. But yeah, it's going to go from I equals 1 to 13. You don't have to start at 0. 0 doesn't do anything. But yeah, it just goes through each of the possibilities for I and j, like I showed in that one, so that the I is associated with maybe the left segment and the j is associated with the right segment. In this case, those segments are represented just by the vector of size 13, and then it just computes the add. So how many times are you going to add these, or how much are you going to add to it right now, which is the number of ways AI times bj. And then you do this thing where you figure out what you're going to, when they're multiplied together, where do they go, modulo 13 that is, and you just add it to that one, and you take the modules, and you return this resulting vector. And that's what it does here. So it combines and it returns a new vector for this node. And you also want to do it when you query, and for the query, I guess you create this res 13. If you pick no elements, you're going to set it to 1, and then here you have to return a vector, and then just swap. Is this vector you return is basically just, you can implement this in a more efficient manner, but it's a vector size 13, so I was like, it's fine. And you just pass in the current result as your left, and then your right as in those left. So it will merge those two or combine them, I guess. And then you want to return res 5 because you want to return it when the remainder is 5. There are a number of ways to have a remainder be equal to 5. And that's it. That's the whole contest. Yeah. So I don't know how much that made sense. I did go fast, and also just kind of getting started at explaining solutions and whatnot. Okay. I don't even know. I'm not even going to publish this one. This is a practice round.